I want to say thank you all for coming out here to my talk. My name is Mitchell Levy. I'm a software engineer at Microsoft. I've been there for about 9 months. And while at Microsoft, I kind of wear two hats. One of them is I'm the WSL kernel maintainer, and then the second one is I spend a lot of time working on the Rust for Linux upstream project. And that's what I want to talk to you all about today, in particular some recent work of mine on bringing the per CPU API that exists within the Linux kernel to Rust and trying to make that API as ergonomic to use as possible from the Rust side of things. So just a brief summary in case you're unfamiliar with the concept of per CPU variables. The key problem here is that locking in atomics are pretty expensive. And atomics also have this drawback where they're really only available for things that are sort of appropriately sized, like machine intrinsics. And so instead of synchronizing across cores to prevent data races, instead we just kind of give each CPU its own variable, and then, well, there's no data races. The key thing here is that we only actually need to do any kind of synchronization when we want to aggregate these variables across different CPUs. And even then, there's some tricks that we can do to not have to do any kind of super heavyweight synchronization there. And so the big thing here is that this is really good for performance critical code. It makes our lives a lot easier. And all of this is basically kind of the same motivation as like thread local variables that exist in user space. It's really kind of very analogous situation here to per CPU variables that exist in the kernel, right? We're avoiding all of this overhead of synchronization by giving each sort of unit of execution its own copy of the thing that we're dealing with. So before I get into the main body of the talk, I do want to have some caveats. All of this is focused on x86 64. Rust for Linux does support other architectures. The work that I'm talking about here doesn't yet. And a lot of this involves a lot of like architecture-specific tricks and optimizations and all of that. And of course, any of that won't transfer over to other architectures. I also want to point out that the Rust for Linux project moves really, really quickly, especially compared to a lot of other kernel subsystems. And all of the work that I'm talking about here is very much ongoing. And so I kind of want to, like the aim of this talk is a little bit different from a lot of the other talks that at least I've personally seen here at scale, where instead of saying like, oh, look at this thing that I've worked on or I made, here's its use cases, here's how you use it, here's why you want to use it. Instead, what I'm aiming for here is to give a flavor of what it looks like and feels like to work on the Rust for Linux project using the per CPU variables as a case study. This isn't meant to be a tutorial on how do I use per CPU variables from my Rust kernel module that I've written. Instead, it's more about like, if you're interested in doing this kind of work, what are the considerations? What are the things that you're thinking about as you work on all of these projects? So with that, let's actually look at how per CPU variables work. This is all stuff that exists right now upstream in the Linux kernel and all accessible from the C side. So each CPU gets its own per CPU area in memory. This is just a block of memory that's set aside, one for each CPU. And the location of that area is put into the GS segment register. And then all of our uses of per CPU variables are all done relative to that GS segment register. So essentially, a per CPU variable is an offset into this per CPU area. So if you have my per CPU var, specifically a statically allocated my per CPU var, you just take the address of that thing, use it relative to the GS segment register, and do whatever you want with it. So in this case, add 1. But who actually uses segmented addressing in the year 2025? Not really a lot doing that, mostly exceptions. But what that means is that if we want to actually make use of this facility, we need to do kind of go around our compiler and talk to the assembler directly with lots of inline assembly and lots of macros that generate lots of inline assembly. And in particular, for any instruction that you want to use and any operand width and any combination thereof, you need to generate the inline assembly that does that, and all of these macros are exactly as complicated as you think they are. And I also want to point out that none of these operations are atomic, right? That would kind of defeat the whole point, at least for our performance critical per CPU variables. And so we want to make sure that we're not switching CPUs at inconvenient points, right? If we want to read a variable add one to it and write it back. We don't want to switch CPUs and then clobber some other CPUs per CPU area with one added to the original CPU's variable. And here's an example of what these macros look like. It can be pretty hard to parse. I cheated a little bit and just looked directly at the preprocessor output to see what was getting spit out here, because there's a lot of macros and a lot of macros that call other macros that call other macros. So if we want to do all of this in Rust, there's kind of an immediate problem here. Macros don't have linker symbols, so we can't call them from Rust, right? The C preprocessor textually modifies the C code that's getting put in, and if we want to use that from Rust, we need an actual linker symbol to point the linker at. So if we wanted to reuse the C infrastructure, the way that we do this with the most macros in C is we write a little helper function that just calls the macro, and then we can link to the helper function from Rust, and problem solved. But as I pointed out earlier, you would need one for each combination of instruction that we care about and each supported operand width. And so there's a gigantic combinatorial explosion of all of the different ones, and that would be challenging to maintain and a gigantic pain to actually write. And there would also be like a tiny amount of overhead here because we'd have to call a function every time we want to do this instead of it all being inlined. And maybe the linker is smart enough to do that, maybe not, but it'd be nice to avoid all of this anyway. So what this means is that we kind of have to do a lot of this ourselves, which is a bit different than what normally happens. A lot of times we can reuse all of this C infrastructure. We can call these functions, use these structures from Rust. But here, there's a little bit of extra work to be done. So I want to start off with discussing statically allocated per CPU variables. So for per CPU variables, you can both statically and dynamically allocate them, just as other areas of memory. But statically allocated per CPU variables serve as a good entry point here because they're a little bit simpler to think about. So static per CPU variables, the way that these work is there is a symbol that you declare in your source file. And this is like quote-unquote fake. You don't want to actually write to this symbol directly because we really only care about its address. And that address is an offset into the per CPU area. And how does all of this work? Linker magic that's outside the scope of this talk. So we're just going to kind of gloss over how that all happens. But the key thing here is that we care about the address of these variables. We don't want to write to the variables directly because it's an offset into the per CPU area. And if you treat that as an actual memory address, you're probably going to have some problems. So what this looks like in C is there's this really fun macro defined per CPU, and you give it a type and a symbol, and then if we want to use that per CPU variable, we have this family of helper macros, including something like this CPU read, which, when expanded by the preprocessor, results in a bunch of inline assembly that results in this single assembly instruction, which does kind of what you'd expect. It takes the address of X relative to the GS segment register and moves it into some register, in this case AX or whatever register is allocated to represent that variable Z. So conceptually, right, from a user interface perspective, this is pretty good, right? We declare a variable the way we're used to, and then we have to be careful to use these macros to make sure that when we access it, we do so in a way that's reasonable. But otherwise, it's all kind of pretty normal. And this brings me to one of the first main considerations of the Rust programming language that we're going to be talking about a lot throughout this talk, which is aliasing rules. So if you're familiar with C++, you're probably familiar with references. Rust references behave kind of similarly to C++ references in concept. It's basically a pointer that is guaranteed to be valid and non-null. But Rust also has these aliasing rules that says that you can't ever alias a mutable reference with either an immutable reference or another mutable reference. You can have as many immutable references as you want pointing to a particular variable, but as soon as you introduce a single mutable reference, that is exclusive and it must be. And the compiler enforces this for safe code. But if you're playing around with per CPU and all of these raw pointers and throwing stuff around with the C side, you need to be careful that anytime you make a mutable reference, you're guaranteed exclusivity, which, of course, if we're talking about stuff that involves synchronization and we want to explicitly avoid as many of these synchronization primitives as possible, becomes a little bit challenging. And in particular, this makes manually juggling pointers and references back and forth pretty challenging to do so in a way that's sound, especially given that All of this is basically just juggling pointers around. A per CPU reference is the current CPU's per CPU area plus the offset of the variable. So we need to prevent users from essentially like doing this pointer arithmetic twice and making these per CPU references that alias each other if any of them are mutable. So how do we get around this problem? What do we do? Well, first, we need to find a way to actually declare these per CPU variables. And so the work here is pretty similar to the way it works in C. There's a Rust macro defined per CPU that takes a symbol and a type and an initializer, and it expands into all of this stuff. There's a couple of things that I want to call out. First off, we have this special extra init symbol. This is not something that you see in the C version of all of this, but the reason why it exists is because this expression here is provided by the user. This could be any Rust expression. And, well, if we expanded it down here, it's getting expanded inside of an unsafe block. And for those of you that are unfamiliar with Rust, unsafe essentially turns off many of the compiler's checks related to memory safety and soundness. So we don't want to silently expand this expression inside of an unsafe context if we can avoid it, because that would allow the user to accidentally do a bad thing inside of there. So instead what we do is we expand it here outside of the unsafe context and then use that value to initialize our per CPU variable. And this is like a kind of like macro hygiene in Rust to some extent. And this link section is related to that linker magic I kind of pointed at earlier and hand waved away. So then, once we have this symbol, the way that we use it is from this fun type called a per CPU ref. And through the magic of operator overloading, this behaves similar to a T reference or a mutable T reference in Rust. And it is basically just a thin wrapper around this offset and a RAII CPU guard, which again, if you're familiar with C++, will feel pretty familiar. Basically, just for the lifetime of that object, as long as you have an instance of it, you're guaranteed that CPU preemption is disabled, and then as soon as it's dropped, you can re-enable CPU preemption. And so the way that we use these is we take the address of our symbol, and we pass that into our per CPU ref constructor along with our CPU guard new. And this is all conveniently exposed to the user via this nice unsafe get per CPU ref macro. And you might be wondering, well, how do we get around that problem we discussed earlier where we don't want any aliasing mutable references? And the answer is, well, we make the user deal with it. That's what this unsafe block is saying. This macro here says, in order to use this macro soundly, you can only call it once. And then the per CPU ref that you get is basically all you have. And then the Rust compiler is able to do all of this for us because it won't allow you to convert it into two mutable references at the same time. So it lets, to some extent, it's dodging the problem a little bit, but it also allows the Rust compiler to help out and make sure that this per CPU ref that we return back isn't misused. But we just need to be careful that there's only one that corresponds to any per CPU variable at a time. And in practice, this isn't too hard of a condition to satisfy, especially for statically allocated per CPU variables. Which brings me to dynamically allocated per CPU variables, and this one's a little bit nicer in that we can actually reuse some of the C infrastructure. There's this nice alloc per CPU function. It gives you a per CPU pointer, and that's a function. We can call it from Rust. That makes our life a lot easier, so we don't have to re-implement all of this allocation strategy in Rust. And a per CPU pointer is just an offset, and this is, again, analogous to the address of a static per CPU symbol. And you also need the size and alignment of the type and all of the other fun allocating things that we have to deal with when allocating memory in the kernel, but again, that's kind of outside the scope of this talk. So what we do here is we store this allocation inside of a per CPU allocation type. And, well, we just talked about this nice helper type per CPU ref. Why not use that to store this allocation that we've made? Well, we want to, again, have the Rust compiler help us out as much as possible. Rust does consider leaking memory to be a safe operation, right? It won't crash your program, so it's OK if you leak memory according to the compiler. But we still want to avoid it if we can. So again, we use this sort of RAII type that says that when this per CPU allocation T falls out of scope, we free the allocated memory. And again, the compiler helps us with this. There's no need to track all of your exit points from a particular function. The compiler says, OK, when this goes out of scope, we just free our allocation, and it's done. So there's no chance that you're going to like, miss a particular ordering through your function and forget to free something. But we don't want all of this to happen if we're talking about a statically allocated variable, and that falls out of scope. We want to be able to continue to use per CPU ref for statically allocated per CPU variables. We don't want to have these kind of like dueling types. And we don't want this to happen if another CPU is still using the allocation. So that's something that we're going to need to handle ourselves. And we also don't want any uses of the allocation to live longer than the allocation itself. So we need a way to keep in mind, hey, if you're deriving a per CPU ref from this allocation, that ref can't live longer than the allocation itself. We need that to be dropped first, and then the allocation can go away, and the underlying memory can be freed. So what does this look like? The sort of drop part, or like, analogous again to a C++ constructor, is pretty straightforward. We just implement this drop trait on the per CPU allocation and says, okay, the compiler will automatically call this when we go out of scope, and then we just call, again, the free per CPU function is provided by the C side, and it's a function, so we can link to it just fine, and we just do some typecasting to make all the types line up and make the compiler happy. And again, the per CPU allocation, all it's storing is this usize offset. It's a very thin wrapper. And then when we want to actually use a per CPU variable, we have this type per CPU t. And this is a reference counted per CPU allocation. And so we can then use this get function to convert between our per CPU t into a per CPU ref. And the reason why this is ref counted is, again, to solve that problem where we need to make sure that if another CPU is using this per CPU variable, we don't like prematurely free the memory on a different CPU and then have a use after free. You might be wondering, hey, I thought the whole point here was to avoid synchronizing across CPUs, right? This is a heavy, expensive operation. We want to avoid that. And yes, that's true. So this ref counting does introduce some overhead here. But this is going to be bounded by the number of times you have to copy this per CPU allocation onto another CPU. You don't actually need to deal with this ref counter every time you want to change the underlying variable, only when you want to add a new reference to it. So the actual performance impact here is not something I've measured, but probably pretty small. And we'll get to, we're not at the point in this work where we're doing serious benchmarking. This is more of a proof of concept. But the hope is that this is an acceptable amount of overhead, and the per CPU allocation is still exposed to end users. So if they have their own way of managing use after freeze, they can do that themselves. This is just sort of a nice, sensible default way of handling it. This does, however, have a problem, and this is related to what I said earlier. If we derive a per CPU ref from our per CPU, and then drop the allocation, or well, drop the per CPU that's holding the allocation, and then we still have this floating ref that we can still use. And this is a use after free, and obviously a pretty big problem that we'd like to avoid. And so now I'm going to introduce a Rust language feature that a lot of newcomers to the language find a little challenging, but hopefully this example will demonstrate why it's really useful, and probably something that you're already kind of thinking about subconsciously if you're writing in C, and that's lifetimes. So in C, there's always this sort of implicit relationship between an allocation and the uses of that allocation. If you allocate some memory and you stick it in a struct, and that struct is floating around for a long time, you can't free the allocation that you have a pointer to in the struct until you either overwrite the pointer in the struct and you're no longer referencing that allocation, or the struct itself goes away. They're kind of linked to each other in terms of how long one can live versus the other. And in Rust, this relationship is made explicit using lifetimes. And that's a little bit of an overstatement, because there are lots of implicit lifetimes. For the most part, Rust does a lot of this for you and manages it for you. But sometimes when you're juggling around raw pointers and doing all of the stuff that the compiler can't help you with, you need to help the compiler a little bit and tell them, like, no, OK, here's how these types are related to each other temporally. So lifetimes look like this little apostrophe and then an identifier. Typically, they're just like one-letter identifiers, similar to like generic types. And so what this is saying here is that per CPU ref is going to be bounded above by the lifetime A. And so when we construct a per CPU ref, we give it a lifetime. And we say, OK, your existence is bounded above by the lifetime that we're passing in. And this is passed in as a generic type parameter. And so then when we actually construct one of these things, we use the lifetime of the per CPU that we're sort of operating on as the lifetime of our per CPU ref. And so what we're saying here is that the returned per CPU ref can't live any longer than its associated per CPU allocation, sort of by extension of the fact that that lives inside of this per CPU, which lives for this amount of time. And this actually lets the compiler catch that error that we made earlier, right? We borrow num, and it actually kind of, the compiler like flips the logic here where it's saying, you're getting rid of num too quickly rather than you're using num ref too long, but these are sort of dual to each other. It's really kind of just saying the same thing here where we are, basically our lifetimes are messed up. We're getting rid of num before we're able to, or conversely, we're using num ref too long. So this is all well and good, but what about statically allocated variables, right? Like I said earlier, we want to continue to use per CPU ref when we're referring to our statically allocated per CPU variables. Well, what lifetime should they use? And the answer is the Rust language has a built-in lives forever lifetime called static, and this is just essentially unbounded. So we can give static as the lifetime parameter for our per CPU ref when we're handling those, and the compiler just essentially handles it just fine. These can live for as long as they want, and the compiler won't ever complain that they're going away too quickly. So, remaining work. There's lots and lots of stuff still to be done on this. This is mostly a proof of concept at this point, but it does show that this work is plausible and able to be used safely from Rust with sort of a hopefully minimal amount of unsafe code, though certainly there are improvements to be made. There's also lots of optimization work to be done here. The per CPU subsystem is used in performance critical code, so we want everything to be as optimized as it possibly can be. And this means lots of numeric types floating around and lots of pinhole optimizations that exist on the C side when you're handling numeric types that we also want to emulate. So like rather than doing a read, add, write back for numeric operations, you can just use a single add sub, et cetera, instruction that does that all in one instruction. Whereas right now, we're kind of copying it over and manipulating it and writing it back. This also needs to work on a whole bunch of other architectures, all of which have its own architecture-specific tricks and optimizations that need to be handled on the Rust side as well. And certainly, there are plenty of bugs waiting to be found in my implementation that I'm sure the people on the mailing list will be oh so happy to point out. And yeah, so there's lots to be done here, but this is a really exciting place to be working. And if you're interested in working on the Rust for Linux project, I hope that this talk has given some insight into the sorts of considerations that go into doing it. There's a lot of sort of implicit, informal rules on the C side that you need to think about and plan for very explicitly when you're writing Rust. And I think that this helps build a really solid, strong understanding of what's actually going on in the kernel on the C side, because it requires you to know all of these rules that are sort of in between the lines of the documentation. For upstream, the Rust for Linux maintains a GitHub, and there's an issue tracker there. There's also a Zulip chat that you can join, where there's a super friendly community that are happy to help out and are really excited for people who are getting involved with this work. And my talk ran a bit under time, so I have plenty of time for questions if you'll have any. Thank you.
So, great talk and very nice work. It's good to see. But I see you're kind of doing, like, Rust and C are both kind of doing their own entirely different thing. So is there any facility for passing per CPU variables back and forth between Rust and C?
Yeah, so there is for statically allocated per CPU variables. I don't have that facility for, okay, well, in theory, right, all of this is pointer arithmetic. If you have a per CPU offset anywhere in Rust, you can just, like, shove that into the this per CPU ref : new and use it the way you want, and that will work. But like I said, there's a lot of concerns around aliasing and all of this that are really thorny to get right if you also have a per CPU ref that exists on the C side. And the compiler does a lot of pretty aggressive optimizations based on its assumption that if there is a T reference that exists, it's not going to change. And likewise, if you have a mutable T reference, only your changes are possible, and there's no other mutations that are happening. So if those guarantees aren't upheld, some of the optimizations that Rust does can break things in very interesting ways that are difficult to debug. So yeah, TLDR, it is possible, but will probably require a lot of very careful reasoning, and it would require relying on a lot of non-local properties in the sense that changes on the C side in entirely unrelated areas could break your Rust code really, really badly, so it's not something I would encourage.
Do you know of anyone using your changes in production that you've implemented in the last year?
God, I really hope they're not using this in production quite yet. No, so this isn't even in the kernel mainline at this point. This is, like I said, kind of proof of concept level work, and I am aiming for mainline inclusion, hopefully soon-ish, fingers crossed. But no, not being used in production, and at least I sure hope so.
Is there a particular kernel subsystem use case that you think this is very compelling for, or a specific project or thing that downstream Rust users you think you will have a real strong benefit to this?
Yeah, so part of my sort of overall goal in my role at Microsoft is to bring Rust to a lot of the Hyper-V paravirtualization stuff. We're still a long ways off from that actually being a reality, but that is kind of a driving motivator behind some of this work. And of course, I mean, really any time that you're doing stuff profiling, if you want to have a hit counter on something, your profiling isn't going to be very good if now you're introducing a whole bunch of other extra locking and atomics to make that, counter actually accurate. So that's a really compelling use case here, and I mean, you can really put that just about anywhere you want to take those measurements, as well as any kind of CPU local stuff that isn't necessarily performance critical, but logically makes sense, where it's the currently running thread or currently running process. That all really makes sense to be a per CPU variable, and so as we build out those abstractions in Rust, hopefully this will be a sort of solid foundation for that work to start on.
We're done? Last chance. Great. Very nice.